Next is equivalence classes. Suppose we take a relation R in set X, which can be represented as R from set X to X. This R is an equivalence relation which will subdivide the set X into the number of partitions, and these partitions will satisfy the following properties. Number one, all elements of a partition, suppose we represent this partition by AI, it is the ith partition, and all elements of these partitions are related to each other for all I. Second is, no element of a partition, say AI, is related to any element of some other partition, say AJ, where AI is not equal to J. And third one is that if we take the union of all the partitions, that means A1 union A2 union and so on, it will give the original set X. And if we take the intersections of these two sets, say A1 intersection A2, it will give phi. Similarly, if we take the intersection of A2 with A3, it also gives phi. In general, we can write AI intersection AJ is equal to phi, where I is not equal to J. So subsets of the set X which satisfy these three properties will be called equivalence classes. Let's suppose we take an example that we are given a set X which is a set of integers represented by capital Z, and relation R in the set of integers is that it is ordered pair AB, where difference of A minus B is divisible by. So this relation, which is an equivalence relation, will subdivide the set of integers in two subclasses, which are the equivalence classes. One are related with 0. For example, the elements are 0, plus minus 2, plus minus 4, and so on. And another is the equivalence class 1, in which elements are plus minus 1, plus minus 3, plus minus 5, and so on. This 0 can be represented as 2r also. We can represent it with 2r, and this equivalence class 1 can also be represented by 2r plus 1, where r belongs to the set of integers. Similarly, if we take another relation in set of integers, X is the set of integers Z, and relation R is such that the ordered pair AB, in which this A minus B is divisible by 3. So here we will have the three equivalence classes related as with 0, another is related with element 1, and third one is related with element 2. These can also be represented as 3r, 3r plus 1, and 3r plus, where this r belongs to set of integers. We can write the elements as this is 0, then 3, 6, and so on, and minus 3, minus 6. So if we take the two elements and take their difference, the difference will be the divisible by 3. Similarly, if we take element 1, the next element will be 4, then 7, and previous element will be minus 2, minus 5, and so on. Third equivalence class will be related with 2, so another element will be 5 by adding 3, then 8, and so on, and previous element will be by we add minus 3, so it will be minus 1, then minus 4, and so on. So these three are the equivalence classes for the set of integers if the relation is a minus b is divisible by 3. That means this relation subdivides the set of integers in 3 equivalence classes.